Hi, welcome back. Now, in the last video, we completed 2D stressor problem. Now, we are going to move to the next type of problem is thermal analysis problem. Till now, we deal with the static stress structural problem, that is bar, beams, trusses, plate with a hole, all those things. Now, we are moving to the next part of analysis on this analysis lab, that is thermal analysis. Thermal analysis means it is when the member is subject to a heat. So how this heat transfer taking place on a body, so that we are going to analyze. Like, we are going to find the what is the heat rate, heat flux. So to analyze that, we are going to it comes under the problems comes under thermal analysis type of problem. So this is FEM. Ansys is a FEM type of FEA package software. So it is a, it this is the kind of feature that we can analyze any type of problem, like maybe structural, thermal, as well as next part what we are going to discuss, that is dynamic type of problem. So now we are going to take up this thermal type of problem now. So here, as I told you, heat transfer type of problem we are going to deal with here. So specially application of these problems will be like an engine, or it may be a, when the body is exposed to the sunlight, how this heat transfer take place. So or it may be in a, aerospace components. So where and the heat application comes to find that heat transfer rate, heat flux, we are going to use the thermolysis problem. So here, as we know, heat transfer takes place in mainly three mode. One is conduction, convection, one more is radiation. Conduction means between to the heat transfer takes place between the solid one body solid body contact with another solid body. So whereas convection means when the heat transfer takes place between the fluid to the solid body. Whereas radiation means the heat transfer takes place with electromagnetic rays without any media. That is usually sunlight. We are getting is heat from the sun using a radiation. So that type of problem we are going to solve it here. Let me look to the first problem. The problem is a composite wall problem. That is, composite wall means it is made up of more than one material. A composite wall consists of three material. The outer temperature is 20 degree. Convection heat plus and the inner surface wall, that is T infinity at 800 degree, and H is nothing but heat transfer coefficient, the convection heat transfer coefficient, that is 25 watt per meter square degree centigrade. And determine the temperature distribution in the wall. Take K1 as, that is this wall is made up of one material that is having K1 conduction. K is nothing but conduction, thermal conductivity. So that is 30 watt per meter degree centigrade, and K2 is 50 watt per meter degree centigrade, and K3 it is 20 watt per meter degree centigrade. So this is a figure. Now in this composite wall, we are talking left side edge as inner edge, and this is as outer edge. So this is, the temperature is 20 degree, and here the temperature is around 800 degree centigrade. Now when this heat, always we know heat transfer takes place from higher temperature to the lower temperature. Therefore, heat transfer from inner edge to the outer edge. When the heat transfer takes place between these two, uh, that is a composite wall. So, what is the temperature distribution take place at this junction between K1 to K2 or K2 to K3? Sir? Hmm. So we need to find the temperature distribution at these junctions. So now we can observe here. Here they are shown the arrow mark on the inner edge. That means here heat transfer taking place. That is convective type of heat transfer. There is some fluid is flowing through that fluid. Fluid having a temperature of 800, and convective transfer heat transfer is 25. And through that, the when it is fluid is contact with the solid body, heat transfer take place through convection. And again this solid body to the next solid body, that is K1 to, it is having material property K1 thermal conductivity, and K2 there is heat transfer. So as you pass it to the next element, what is happened, because of resistance it is observed some temperature, the temperature is going to be decreases. And finally when the heat transfer at this outer edge become 20 degree. So that means 800 to 20 minus 800 minus 20 means almost 780 degree it is observed by the each element. So now we need to, how much heat temperature at these junctions, that we need to find. So for that they are given the width of the heat wall here, 0.3 meter, 0.15 meter, and 0.15 meter. So let me get into the answers to execute this problem. So now here very important thing, preference. In that we need to select a thermal now. Till now we selected structural, but now we are dealing with the thermal stress versus problem. Therefore preprocessor element add. Now we need to here when we selecting this add, we need to select a here link element. In link there are different elements like conduction, 3D conduction, convection, radiation. Now there is a conduction will be there. How many conductions? Conduction taking on the three elements. Therefore given K2, K3 will be there. Therefore we need to select three conduction. Apply, apply, apply. Also there is a convection. Press select convection, then press OK. So there is no radiation. Therefore totally we have to select four elements. Now we need to assign a real constant for this add. So you have to very important step here. Carefully you have to select one by one and you have to assign the real constant. Let me take link 1, link 2, link 32 or conduction, link 34 is the convection. Let me select the link 32. Then what is the area itself? So area is not given. Let me take to the unit area. And now add 2, that is also unit area is 1 meter square, and add link 3 and that is also area is 1. Then add select link 34, and what this asking is it is asking the area and leave it about empirical coefficient as well as input constant. So now we given a real constant. Now we need to select a material models. This is very important. So we have three different material and three different property will be there. Therefore we need to create a three conduction type of property we need to give along with that convection. Therefore there are totally four material model we need to create. For that thermal you have to click it conductivity. So when you, because we selected thermal conductive problem in previous structural we are getting like isotropic linear Young's modulus C2S, but now we need to say thermal property. So now conductivity is a thermal property. In that first move let me give the K1 value. So K1 value is 30 watt per meter. Everything can be in meter only. Press OK. Now let me select the next model, create material, new model, ID number 2, OK, K2 value. K2 is 50. Now go to material model, OK. Now that will be K3 is 20. Also we need to give a convective heat transfer property, that is material number 4. Here you have to select the convection film coefficient, that is H value 25. So totally there are created 4 material models. That is very important. Next we need to create a modeling. Here as usual we are going to create like a modeling like directly with the nodes and elements like a 1D type of problem. So therefore modeling create nodes. So let me see the node condition. How many elements we need to create? So here there are 3 different elements, therefore 3 elements we are going to divide. So here node 1, node 2, node 3 and as well as node 4. And one more thing is we are going to addition to this we are going to create one more element with respect to the convective heat transfer, that is imaginary element. So that will be taking the width as our own assumption. So again take 1 meter, 0.1 meter as a, with respect to these values we are going to taking like a 0.1. So now this side it is origin we are taking is left side become negative. So totally 4 elements we need to create. Here node 1 0, 0, 0, here node 2 0.3, 0, 0, and node 3 0.3 plus 0.15, 0, 0, and node 4 0.3 plus 0.15 plus 0.15, 0, 0. And addition to that we are taking one more imaginary element here with a width of 0.3, so to indicate the heat transfer coefficient convection. So let me model this nodes in active CS. Apply, taking the second node. Second node is 0.3. Everything we are taking in a meter. Apply, then 3 then 0.15. Apply, then 4. So fourth node is here plus 0.15, and one more, as I said you, fifth node it is on the left side, imaginary node. So therefore that will take it as minus, because origin we taken here, right is positive and left is negative, that is minus, and we are going to take up that element which assumption is minus 0.1. You can take any length, so always choose with respect to the this range only, width of this plate. So I'm going to take as minus 0.1. Now totally there are 5 nodes created. Now joining these nodes by elements, auto number through nodes. So here very important thing is material attributes we need to select, like in a stepped bar problem. First we are going to give a 1 to 2 we are going to join. Therefore link 1 is conduction, material properties 1 and real constant 1. Therefore through nodes we need to join 1 to 2 plus apply. Then again element attributes. Now for the second element it is conduction property, material number is 2 and real constant is 2. So through nodes 2 to 3 press OK. Again element attribute, third element, that is K3 property, we need to select. Therefore element 3 and real constant 3, press OK. Through nodes 3 to 4, press OK. Now finally we need to join from 5 to 1, it is convection. So convection element we need to select, that is link number 4, and here material model is 4 and real constant is 4. So therefore through nodes 5 to 1. So you can observe now it is all indicating different color, means different property. So this is very important stuff. You've done mistakes here, finally get a wrong answer. So make sure that you are given correct alternative property. Now we go for boundary condition. Solution, define loads, apply, thermal, temperature on nodes. Keep this in mind. We are going to apply a temperature, and this node press OK. That is temperature will be around T infinity 800. Yeah, press OK. And yeah, this is a, so this is the thing, we need to apply boundary conditions on this. I think there is no need for convections and okay, so that's all. Now pre-process part is completed, it ready to solve this. Press yes. Now we need to view the results. To view the results we go for general post plus list results, nodal temperature we need to check. So here we having a nodal solution, DF solution and nodal temperature. So now we get in check out here node 1. So where is the node 1 is selected? Node 1 is here. So node 1 is 284 here. So let me validate. Node 2 is 155 degree, node 3 is 116, and node 420 we already given the dimension, that is boundary condition 20 and 800. So our answer is right. So by this we completed the first problem on the thermal system. I hope you are understood. Thank you.